Hello! I'm Professor Von Schmohawk, and welcome to YU. In the last several lectures, we have seen how to perform arithmetic operations on complex numbers, including the operations of addition, subtraction, multiplication, and division. In this lecture, we will see that just as real numbers are the input and output values of real-valued functions of a real variable, otherwise known as real functions, complex numbers are the input and output values of complex functions. Complex numbers, built upon the concept of imaginary numbers, were first proposed back in the 16th century in order to calculate solutions to certain types of equations that were unsolvable using real numbers. Although this may have started as a purely academic pursuit, since that time, complex numbers have become indispensable in many areas of engineering and science. When we first introduced complex numbers, we showed that quadratic equations that have no solutions when only real numbers were considered do have solutions if we extend our number system to include complex numbers. For example, the quadratic function x squared plus 6x plus 10 can be defined as a real function or a complex function, depending upon whether we want to limit the input and output to real values or allow complex values. When dealing with complex functions, the letter z is typically used instead of x to represent the complex variable. As we have seen in previous lectures, a quadratic equation is a mathematical statement that says that the output value of a quadratic function must be equal to 0. The solutions to quadratic equations are therefore values of the input variable that cause the function to produce an output value of 0. In the case of real functions, these x values correspond to the places that the function's graph intersects the x-axis. Therefore, a real quadratic equation in a single variable can have two solutions, one solution, or no solutions. However, this is only true if we limit the input values to real numbers. If we include complex numbers as possible values for the input variable, then there are two solutions that cause the output value of this function to be 0. In the lecture Imaginary and Complex Numbers, we calculated this equation's solutions -3 plus I and -3 minus I. Once the solutions to an equation have been determined, we would like to check those values by substituting them back into the original equation to see if they produce a true statement. However, in that lecture, we had not yet seen how to perform arithmetic operations like addition and multiplication with complex numbers, so we had no way of confirming our results. But since in the last several lectures we have seen how to perform these operations, we now have the mathematical tools we need to check these solutions. We will start by checking the first solution, -3 plus I, replacing z in the quadratic equation with that complex value. To square -3 plus I, we write it as -3 plus I times -3 plus I, and then multiply using the distributive property. -3 times -3 is 9, and -3 times I is -3i. I times -3 is negative 3i. And I times I is I squared, or negative 1. Adding these results, 9 minus 1 is 8. And negative 3i plus negative 3i is negative 6i. Next, multiplying 6 times negative 3 plus I, we get 6 times negative 3, which is negative 18, and 6 times I, or 6i. Now we add these results, plus the remaining term of the quadratic function. Adding the real terms, 8 minus 18 is negative 10, plus positive 10 is 0. And adding the imaginary terms, negative 6i plus 6i is also 0. So substituting the first solution, negative 3 plus I for z, causes this quadratic function to produce an output value of 0, causing the quadratic equation to produce the true statement 0 equals 0. Since substituting negative 3 plus I for z produces a true statement, we have confirmed that negative 3 plus I is indeed a solution to the equation. Now let's validate our second solution, negative 3 minus I. Once again, we replace z in the quadratic equation with our solution, negative 3 minus I. Squaring negative 3 minus I, we write negative 3 minus I times negative 3 minus I and multiply. Negative 3 times negative 3 is 9. And negative 3 times negative I is positive 3i. Negative I times negative 3 is positive 3i. And negative I times negative I is positive I squared, or negative 1. Adding these results, 9 minus 1 is 8. And 3i plus 3i is 6i. Next, multiplying 6 times negative 3 minus I, we get 6 times negative 3, or negative 18, and 6 times negative I, or negative 6i. We now add these results, plus the remaining term of the quadratic function. Adding the real terms, 8 minus 18 is negative 10, plus positive 10 is 0. And adding the imaginary terms, 6i minus 6i is also 0. So just like the solution, negative 3 plus I, substituting negative 3 minus I also results in a value of 0 for the quadratic expression. Once again, this produces the true statement 0 equals 0. We have now confirmed that both input values, negative 3 plus I and negative 3 minus I, are valid solutions to the quadratic equation z squared plus 6z plus 10 equals 0. This tells us a little about this complex function. Although we don't know much else about the characteristics of this function, we do know that the input values, negative 3 plus I and negative 3 minus I, produce an output value of 0. Since these are the only two solutions to this equation, we also know that all other input values must produce output values that are not 0. As an example, let's try an input value of 3 plus I, which is not a solution. So let's replace z in the quadratic function with 3 plus I to see what output is produced. Squaring 3 plus I, we write 3 plus I times 3 plus I and multiply. 3 times 3 is 9, and 3 times I is 3i. I times 3 is 3i, and I times I is I squared, or negative 1. Adding these results, 9 minus 1 is 8, and 3i plus 3i is 6i. Next, multiplying 6 times 3 plus I, we get 6 times 3, or 18, and 6 times I, or 6i. We now add these results, plus the remaining term of the quadratic function. Adding the real terms, 8 plus 18 is 26, plus 10 is 36. And adding the imaginary terms, 6i plus 6i is 12i. So an input value of 3 plus I, which is not a solution, produces a non-zero output value of 36 plus 12i. We could continue calculating output values for various inputs to try and get a better idea of the characteristics of this complex function. However, to get a more intuitive view of this function's characteristics, it would be helpful to graph its output versus input over a continuous range of values, as we do with real functions. Real functions can be graphed on a two-dimensional plane. Since real values can be represented as positions on a one-dimensional number line, the input values of a real function can be represented as positions on the horizontal axis, and the corresponding output values as positions on the vertical axis. These pairs of horizontal and vertical positions then define a set of points on a two-dimensional plane that we call the graph of the function. However, since it would take 2 dimensions to graphically represent complex input values, and another 2 dimensions for the output values, it would require 4 dimensions to graph the relation between a complex function's input and output values. Since 4-dimensional graphs are not feasible in this universe, mathematicians have come up with a number of ingenious ways to represent the relation between these two sets of 2-dimensional values. For instance, the input values can be represented as points on the 2-dimensional complex plane, and the corresponding output values can be represented as the color and brightness of those points. As an example, let's say that for a particular function, an input value of 4 plus 3i produces an output value of negative 3 plus 2i. The output point's location on the complex plane would then be mapped to a particular color and brightness by superimposing a color wheel on the complex plane. A color scheme such as this one associates brighter colors with output points closer to the origin. The color and brightness corresponding to that output point would then be assigned to the input point that produced it. So if we think of the output values as vectors, as we have seen in previous lectures, then the brightness of a point would correspond to the output vector's length, otherwise known as its modulus, and the color of a point would correspond to the output vector's angle from the positive real axis, otherwise known as its argument. If we color every input point according to its output value, the graph of the function becomes a color map of the complex function's output values. This process is sometimes called domain coloring. Another way that the inputs and their corresponding output values can be represented is to graph a subset of the input values that fall along some path of the complex plane. For example, we could pick a path of input points along a horizontal line extending from -5 plus 3i to +5 plus 3i. We then graph the corresponding output values of the function on a second complex plane. For f of z, let's use the quadratic function from earlier in this lecture, z squared plus 6z plus 10. Since this function generates much larger output values than our input values, we will choose a scale for the output graph that ranges from -50 to +50. Now for each input point, we will graph its corresponding output. The path we choose in our input space doesn't have to be a line. For instance, we could choose a circular path. Or we could choose a square path. By graphing multiple input paths with slightly different parameters, we can get an even more intuitive idea of how the input and output values of a function are related. For instance, using the same function, let's start with a subset of input values that form a linear path. Now let's do the same for a second subset of input values that form a path parallel to the first path. If we continue to do this for more input paths, we can get a better idea of the behavior of this complex function. Notice that at this point, the curved output path has collapsed into a line that doubles back onto itself. Now, as we continue to graph more input values that form parallel paths, an interesting thing happens. The additional output curves retrace the previous output curves, but the points appear in reverse order from the previous curves. Notice that two of the input lines pass through the solutions to this complex quadratic function, -3 plus I and -3 minus I. As a result, the output curve that corresponds to those two lines passes through the point 0, 0, which is the point where the complex quadratic function is equal to 0. And the fact that for those input values the function's value is 0 is why those two values are solutions to the equation z squared plus 6z plus 10 equals 0. We have seen that the solutions to quadratic equations are values of the input variable that cause the quadratic function to produce an output value of 0. In the case of real functions, these x values correspond to the places that the function's graph intersects the x-axis. And since the graphs of real quadratic functions are parabolas, the function may have two solutions, one solution, or no solutions. However, quadratic functions are just one example of a broader class of functions called polynomial functions, whose graphs can have much more interesting shapes and therefore many more solutions. In the next several lectures, we will explore these polynomial functions.